Fotukatoa Morena. Welcome to this webinar on enhancing code reusability using containers to port an atmosphere ocean-coupled model on NeSI. We have 3 speakers amongst us today. Dr. Alexandra Gossart, who is a climate modeler at Victoria University of Wellington for Antarctic Science Center, and the National Modeling Hub for the Antarctic Science Platform. Dr. Alena Malyarenko, who is an ocean modeler at the University of Canterbury and the National Modeling Hub at the Antarctic Science Platform. And Dr. Alexandra Pletzer, who is a research software engineer helping New Zealand's researchers run better and faster platforms. Faster research on NeSI platforms. Welcome. So before we delve into all of that, I do want to begin with a quick round of housekeeping notes. Please note that this webinar is being recorded. Do make sure to mute your microphones. This is just to minimize any sort of background noise. And also there is a QA doc, which we will be using through the course of this webinar. I will share the link on chat now. Please feel free to use that to capture any comments or questions you might have through the course of the webinar. We also have the Zoom chat. If you have any specific questions, you can send them to everyone and not to one person, which will make sure that all of us are able to see it at the end when we'll take questions and comments. So with that, I hand over to Alex to speak to us about the consultancy service at NeSI.
Thanks. I wasn't quite sure which Alex, so I was
sorry.
sort of waiting
Alexander
until
Pletzer.
you.
Yeah.
Yeah. So we, some people may be aware of that we at NeSI we not only have machines and computers and hardware and GPUs and what have you for you to run as scientists to utilize those resources, but we also have human resources, and that these come in a variety of ways and shapes. Training is certainly one of them, and we have app support, but we also have a consultancy service, which I'm just mentioning here because I know that some people who are attending actually the presentation today will likely work with us at some point or have worked with us in the past, but others may not be aware of those services, and these can be anything from workflow parallelization, software parallelization, code optimization, improving I/O performance, porting to GPU, software sustainability, but also now we have data science, which is a big thrust at NeSI and elsewhere. And so we have a data scientist, Maxime Rio, who's also an expert in these areas. In fact, the presentation will be about a consultancy that we performed for 2 researchers. I think the main message is that the platforms that we offer for researchers to do their work can be sometimes hard to use, and we're here to help researchers and scientists get as productive as possible. And so the way to contact us, you can just send an email to support@nesi.org.nz, and that's a good way to get into contact with us, but otherwise we also have a web page. If you just Google for NeSI consultancy, then you should end up on a web page where you can see a little bit our activities, and some can be seen in the case studies that we publish.
Thank you, Alex. I will stop sharing my screen now and hand over to Alena.
We all on full screen? Excellent. Thank you, Misha. So we are using coupled models, and they're quite complex. And the question that Alex posed to me is, why are you even using coupled models in Antarctica? And for those who don't really work there, it's an interface between atmosphere, ocean, ice shelf, sea ice, and then the cavity is the interface between ice shelf and ocean and the bathymetry. So there is lots of processes that all depend on one another. So for example, as the winds blow off the ice shelf, they move the sea ice away from the Antarctic ice shelf coast. They open it up and create the area known as Polynya, which is the area where lots of new sea ice is in turn produced. And via brine rejection, it completely changes the structure of the ocean, and that water can flow then into the cavity and enhance the melt or lower the melt rates of the cavities. So to understand how the melt rate is happening, for example, here at the grounding line of the Ross ice shelf, we do actually care really much about how exactly those winds are blowing on the ocean. And those coupled processes are only really being captured when all of the models are run simultaneously. So what is needed to run a coupled model in general? You need a model code. So there is some Fortran and some C pre-processing flags. You need a bunch of tools to set it all going. And then you need all of the software libraries, which are mentioned at the time of compilation, and they're used to handle different data formats and to obviously do MPI things. And then all of these code and tool and software libraries are running on your local friendly supercomputer, and so they're obviously supercomputer dependent. So what exactly is a part of our coupled model? We have three separate things. So the atmosphere is run with PolarWRF, so Polar Weather Research and Forecast Model. And then the ice sheet, sea ice, and ocean I run with MIT GCM. This is an ocean global circulation model. And then the thing that's sitting in between those two big models is ESMF, so Earth System Modeling Framework, with a bunch of other letters that make no sense. But all three of them together, wrapped in a nice little package, become Scripps-Kaust coupled model. So when the ESMF, what it does is allows us to run two models simultaneously. So if you're running your single model, for example, you're running your atmosphere model, typically what happens is there is an initialization stage, and then the model progresses in time. So when there are two models here, with explicit coupling, you can see that there is an atmosphere model and an ocean model. They go through their initialization, and then as they start running, they both exchange the data. So stuff from the ocean, for example, surface information goes into the atmosphere model, and then those winds and air temperature and how much rain and snow there is going back into the ocean model. And so models can have different time steps, they can have different horizontal resolution, and every exchange period, they stop and they exchange their information and then they run again. And so ESMF handles both models running simultaneously and that stop a run solution. So now you have a coupled model with code and libraries, except all of these are multiplied by 3 because it's three models pretending to be one big model that is trying to go to the movies. Like 3 dogs in a trench coat is my favorite joke. So, and because it's 3 models here is like, it's perfect solution. So how do we do this? How do we keep track of it? If you've ever run a model, there is some build file, make file list, which has all of the different flags. And so when you run one of these models, you have a long file. This is the top of the file for the MIT GCM, and this is for WRF. And each of these little, what is the coupler name? What are the optimization flags that are working here? Is it a big endian? Is it a small endian? This is all model dependent and machine dependent. And so when we have 3 of the models, obviously this all has to be compiled with the same flags, and they all have to be happy with it, which is fun, as you might imagine. So the way that we're doing is we have our custom Bashar C coupled to run this coupled model. And what we've learned is that we do need to be really careful about what we're loading and the versions. So we've kind of moved on from module load ESMF to module load ESMF with a very specific version. to make sure that we're always loading the same one to make sure that there is stability. And it all worked great, except, machines get upgraded, things change. This version is no longer available, so now we have to find a new version that is also compatible with everything else. So here are some fun examples of starting a model from scratch. We have a 60-page of documentation of all of our failures, which abruptly ends when the model starts running. So we started from a local compilation attempt at our machines, and the same compiler but different year versions. One of the versions worked for 2 out of the 3 models, and one version worked for 3 out of the 3 models. And there was absolutely no sense why there was a difference. And when we switched to Maui, there was just a pure chaos. And if you've ever tried to install something from scratch on Maui, you know that Googling for a Cray environment is incredibly hard because there is not a lot of those kind of machines. And, we now went back to our document and, why did we add the link type dynamic? We don't know. Google recommended it to us. But then, of course, it came back to bite us later. Models have vague error messages. So, this is again a screenshot of our document where we found another problem and we went into the code and the model just says that it's going to whine and die, which is extremely useful for figuring out what exactly is going wrong. So we were trying to figure it out and there was just no error message. It would just say, no, I'm not working. The Friday afternoons was the favorite time between Alex and myself, 6 months of complete insanity where, the model is running and it's producing output, but it doesn't look like anything. Or the model is running and it kind of looks like the raw C, except that one of the variables is weirdly blocky and is not doing anything sensible or physical. But this is, we got to the point of the model running. And then this is one of also my favorite personal screenshots of, we submitted a case and it worked and we've put in a GIFs of a very happy penguin. And then we look at the results and there's just like, the results are completely horrible. So we are obviously not software engineers, but we went from scratch from loading a code that has never been ran on Cray environment to making it run and making it produce actual sensible results and not just this kind of files. And it took us about 6 months in total. So what happens when the machine went down or goes on maintenance? You need to find all new compatible versions of all of the libraries, and you need to remember all of the funky switches that you've introduced and you don't remember why, but you've tried them and they worked. So some things like ESMF, for example, is an easy build, which means that it's just module load ESMF, but the default version was never compiled to support netcdf, which is a main file format for climate models. So we had to log in a NeSI ticket and ask them to recompile and justify why we need them to recompile this easy build. And then in the end, the solution to all of that, and dreading doing this all again, if something happens again, is the consultancy about coupled model containerization, which, as Alex and Chris are telling us as white knights, saving us, is that it's not dependent on the machine, it's not going to be dependent on the updates, and that's a portable code that we all going to be able to use forever and ever and ever. And this is my part of the presentation. I'm supposed to ask if anybody has any questions, but I'm assuming that nobody has questions. But if you can put in a Google Doc how long it took you from model installation to model running, that would be really fun. And with that, I'm gonna hand over to Alex Pletzer.
Hey, thanks, Alena. I'm not sure I like the picture of the knight on the horseback, but we definitely here to help you suffer less. So if there are other scientists or researchers who have suffered from the upgrade that was made last year on Maui because the library versions have changed and so forth, so we would be happy to have a conversation with them. And the goal of this webinar is not to be confined to climate simulations or weather forecasting, but it's sort of more general. If you've been running or compiling your own code on Maui, then perhaps what's going to follow might be useful. So happy to be interrupted at any time, but since I don't see any questions, I'm going to go ahead. And I'm going to talk a little bit about containerization. Some people may not be familiar with the concept and why we think this is a good solution for researchers in general, whether you are in climate science or in another domain. And so traditionally, what's happening is on the left-hand side, you have these stacks of software at the bottom. I mean, you have the hardware, you have the libraries that go with the hardware, you have the OS, other things. Then you have tools and libraries that are installed on the system, and then you have an app or application on top of that uses everything that is underneath. And what happens is that if you have a system update, then suddenly the app may have been compiled with a library that no longer exists. And so it's going to refuse to run after that. And I think that's the source of frustration, I think, of some researchers who had to recompile, rebuild their code, and as you heard from Alena, this could be exhausting process that sometimes would take months. So we're here to help, and we also here to avoid this happening in the future. How can we avoid this happening? Well, by isolating the application and the tools and the libraries and putting them in a container. And that container essentially is a bit like that lighthouse that is shown here on the in the picture. It's surrounded by total chaos. I mean, there's wild things happening. A hurricane is hitting Lake Michigan, whatever it is. But that lighthouse is standing firmly. And is going to be able to operate as if nothing was happening. So that's the goal. Now, containerization is one technology. There are other ways you could achieve that, maybe Conda environment and other things. But we went for Aptena, which was formerly known as Singularity. And think of it as a Docker. If you've been familiar, I heard the term Docker containers. Aptena is very similar to Docker, except that it's more HPC, high performance computing friendly. Next. So the first question is okay, so how do we build a containerized application? So the nice thing is basically you write a recipe. And once you have the recipe, then everything is automatic, it's automated, is recorded. You don't have to take some notes on the, in your personal notebook and go back and skim through your personal notes to figure out how to build the coupled model, any complex build system. And in this particular case, so I'm just going to emphasize, 3 areas here. This is just an excerpt of that recipe file, which is called a definition file. On the top, we're going to start from an existing image, which has already the compilers and MPI, as well as Ubuntu, the Linux operating system installed, but you can start from a different image that would have maybe GCC or other compilers, maybe the NVIDIA compilers. Then typically in blue, what you would do is that you would do system install inside the that particular image so you add your library. So it just happens that we need a wget, which is a tool to get stuff from the web and compression libraries and other things, and they already built for Ubuntu. So we're just using a package installment tool, which is apt in this particular case to install those additional packages. Then the third step is that we building by hand on the dependencies like netcdf, hdf5, and so on and so forth. So you have, you know, you have a wget step, then you have a configuration step, and then you have a make step, and then you install it, and essentially you're done. Next, please. So so this would be, so I talked about the definition file, which is the one in sort of highlighted in olive color. Then what you would do is that you would create an image. So you essentially now you know, on the right hand side in olive you have the recipe, but now you really want the real thing, right? You want the stuff to be built, and so that's going to create a CIF image, a CIF file. This is just a file. You don't have to look into it. It's a file. But the beautiful thing is that this file embodies everything that you need. It embodies, you know, the compilers, the operating system, the libraries, blah, blah, blah. And you can hand it over to your colleagues. You can hand it over to other researchers. If you're running some experiments and you're finding some results, or you're writing some paper and you want to come back in 5 years and run, you know, that special case with where, you know, the Antarctic ice was melting and in the Ross Sea, you know, under some weird condition, you can do that because you would have saved that environment inside that CIF file, but you have to build it. So the way it works is that you would call the obtainer command with build obtainer build. If you're on a laptop, you can do that actually on a laptop if you want to. You'd have to do sudo something, but it's basically just obtain a build. And if on our system, you can also do it. You can build it on the Milan nodes. So there are some instruction we can provide if you're interested, but you have to use the fake root. I think if you search NeSI, obtainer, then you will find these instructions. So this will create a C file from the dev file, and you can share it. And I think that's the main message here. Now, remember that once you create an image, it cannot be modified. It's frozen. So you hand it over to a colleague. The colleague cannot go down into or sort of modify that CIF file and say, oh no, I want to change the netcdf version and so forth. No. You can't change it, so it's going to guarantee that the executable, the libraries and everything that you build inside will just run the same way, and will be a bit reproducible according to they will, you know, the result will not change when you go from one platform to another. As far as we could see. I'm not 100% sure that this is the case, but it looks like it is. Next. So once you have, so you define your recipe. Let's go back. We define the recipe. Now you build your CIF file, which is that container, and then you can execute it. So you can do that in two ways. So again, it's an obtainer command. And by the way, you'd have to do a module load obtainer on our platform on Mahuika. And the other thing that I want to add here is that you can't do that on Maui because Maui has an older operating system, so it doesn't support obtainer. So you'd have to do that on the Mahuika platform. And then you can do shell. And if you do shell, obtainer shell, then essentially you end up being in a system which is very much like a cluster. You're running on Mahuika, but it behaves like a cluster, and I can run a demo afterwards. It takes the CIF file. Everything takes the CIF file after that. Or you can also do obtainer exec, and that means that you're going to execute, run a certain application. And so it takes an additional argument, which is app here, and that could be that ESMF coupler, something, you know, coupled model executable. Now, the nice thing is that when you do exec or shell, it's going to mount a number of directories in the file system, and these would be the no backup and the project directories will be mounted, so you can still access your data and everything. Next, please. What are the differences? You know, in once you have this executable, you have built everything. You know, how do you what would be the difference with Slurm? So here there's a little subtlety that we had to figure out, and it's how to get the application, the containerized application, run on multiple node. And so first we had to bind or mount, you know, the /opt/slurm lib64 because that contains some information about how, you know, Slurm and MPI work together. We also had to turn off the shmem. I'm not going to go too much into the details, but this particular setting, export I MPI fabrics equals OFI, allows essentially us to run on multiple nodes. Now, keep in mind that when you build your application inside the container, you know, this is a very closed environment, and the application doesn't have any understanding of what the MPI how the MPI on the host was configured. So what we're trying to do is to relay essentially all the calls of the MPI inside the container to the MPI on the host in order to be able to run on multiple nodes. We also see the module load Aptena and Intel here, just because we're using the Intel MPI, which so that's the reason. Next. So maybe one question that people might have is, yes, but it's, you know, it's going to run slower, right? Because after all, it's a virtualized environment. And so there could be a penalty. It's just that we haven't seen it. So here are a couple of numbers of execution time. So really the third column is the one that I would like people to concentrate on. And these numbers, the higher the better. They represent essentially how many times faster than reality does the code actually run. Obviously, if we had a climate simulation code that were running slower than reality, then it would not be very useful, would it? So because you might be better off just waiting for climate change to happen before actually seeing your results. So you want that number to be as high as possible. And on Maui, I think if you're running on 3 nodes, you're getting about a factor of 60, let's say just below 60, and this is really using the native compilers and the native environment. There is no virtualization whatsoever. Now, with the Aptena approach, and I'm going to focus on the green row below, we got about the same performance, but actually using only 80 processors, and they were all sitting happily on a node, because on Mahuika extension, the Milan partition, that is, we have 128 cores. So, you know, we still have some cores left over, and some other people, you might still be able to run some more stuff than that. So comparable performance and less resources, fewer processors. Keep in mind that with the Genoa processors, then you're going to have even more cores per node and so forth. So that offers the opportunity again to increase the number of processors. And we have just acquired, Genoa processors now. People, engineers are working hard on setting up the system. I'm not sure exactly how long it's going to take, but everything is evolving. Processors are changing, and the latest one will come online hopefully in sometime in the near future. We also found that actually running on a single node is a good thing in this particular case, because then you don't have to sort of communicate across node, which is always going to be a little slower than inside a node. The Gitesh said something, maybe. I'm not sure. I'm quite happy to answer any question people might have. Otherwise, next slide. So we down to the summary. It's great because that will leave us a little bit of time for live demo. The main message that I want people to keep in their to carry away is that an Aptena or a containerized application, be it a couple model or something else, is a bit like a frozen food. So it's it's already there. It's everything is there. You got the vegetables, you got your meat, you got everything. And it's ready to be served once you fire up essentially the image, and I will show you how to do that with Aptena exec or shell, which would be the equivalent of warming it up in a microwave oven. So I think what we've seen is that it allows you to build once and run almost anywhere. I have to be a little bit careful here because in retrospect, what happens, I think you still need a processor that is Intel related, so AMD or Intel would work. And you need to be a little bit careful when you're using compiler switches, not to use something that is very specific to a particular architecture, because after all, you don't exactly know on which host you're going to run. So that's maybe another area when one could but potentially lose a little bit of performance. But in practice doesn't seem to be a big deal so far. The next thing is that you have to write that recipe, which is just a normal ASCII file that tells you essentially what should be built, what's the starting point and the executable. These essentially list the steps as you would go through manually if you were to build the application yourself. And this image can then be shared with other researchers. You want to use the MPI of the host, if possible, the message passing interface library of the host, if possible. You can use also the one inside, but of course it won't have knowledge of the what's going on, all the nice little features that have been added and add up to the price of a supercomputer in some sense. We talked about the fact that there was no observable runtime penalty, and we also said that it required fairly little change in terms of Slurm scripts. So typically in your Slurm script, you're going to define your resources and everything, and then you're going to have a srun app application instruction at the bottom line. And here you just have to change it with srun aptena exec, with some additional stuff regarding the mounting of directories and so forth. But it shouldn't be a big deal. And just to show you finally that you can start with existing images, and we have one. For instance, if you copy paste that command aptena pool, it will actually get a container that an image that from the web, that will have netcdf and the compilers and MPI and ESMF, and whether you use it or not doesn't matter too much. It's all going to be based on the Intel compiler suite, and you can just download it or point the URL to your colleagues. This could be potentially a good starting point for anybody in need to port the application. Next. So just reminding people that we have a consultancy service, and we encourage people to inquire and see if there's something that we can help. At NeSI, we have research software engineers, we have data scientists and so forth, and we basically try to do the boring stuff so that you can do your research. So we the best collaborations we've seen so far is when we really complementary, as it was the case in for that particular consultancy with Alena and Alex. But these are the particular areas where we tend to be involved. They're not exhaustive, so and there always new technology, new things coming up. So we tend to it's a continuous sort of we tend to educate ourselves so that to meet your domains as researchers. And you can send an email to support, if you have more questions about the consultancy. Next, please. So happy to ask. Maybe we give people one minute or two, for questions, or longer if there are more questions. Otherwise, I'm happy to go and show you a little bit, how things work live. Nisha, is there anything?
Yes.
Sorry. Yeah.
Yes, just checking the QA doc now. Doesn't seem like there are any questions, but that have not been answered. Yes, all the questions have been answered already. Any more questions that people might have? Please feel free to use the QA doc or unmute and
I have one question.
yes, please go on.
Thanks, Alex. That was really interesting. Sorry if I missed this already. I missed the start of the webinar because a load of firewood arrived in a truck at the time at my house. So it looks like the container is being used as if it were the application. Is that right? You don't have to treat it like sort of like a VM, even though it's got all of the OS and everything in it.
I think it's the second. I think I tend to look at it as the experience that that researchers would have. Is having something that looks like a mini little cluster that you're running, and it will have all the libraries, it will have the tools, it will have the executable or not. In this particular consultancy, actually, we didn't build the executable inside the container because there's some licensing issues and so forth. So everything that was open source, we built, and then Alex and Alena just have to run a script to build that executable on top, but using essentially the environment, libraries, tools of the container, if that makes sense. But you could very well also have the application in it installed as well.
Right. So if you do have the application in it, can you then sort of pretend that the entire container is just the application, even though it has everything that it needs with? It needs. Yeah. Right.
Yeah. You could pretend. Yeah.
So in a way, you don't have to know that it's containerized if you're a user.
No, except at the level of Slurm and I can show how that works. Yeah. So maybe this will become clearer when if I'm sharing and I'm running a demo. I can do that now unless there is another question coming up.
Thanks.
Nothing on Google Doc yet. I guess you can go ahead, Alex.
Okay, so bear with me because I'm a very bad typist, and but anyway, I'm on the right hand side. I have I'm connected to my Wika, just the login. I have I'm in a certain directory that has already a CIF file. So we can probably see the CIF file. So it's here, and So what I'm going to do first is I'm going to just enter that containerized environment, and just to show you a little bit, how it feels. So remember that C file basically embodies, that whole virtual environment that was built and downloaded using the command that I just showed, the pull command, which is at the end here. But it takes about 15 minutes to download because it's fairly large. So I spare you that boring part. So the first thing I have to do is I just have to do a module load of Alena. And that will give me access. So this would be the latest version of Alena. There are different versions. I'm making things a little easier here than perhaps you want, but I'm always happy to use the latest version. And then the next thing that I can do is I can do shell, as I suggested, and then just add, that C file. And that will send me into an environment which has NeSI no backup, NeSI project sort of mounted. So where am I? I can still type pwt. I haven't actually tried that, but it's probably Ubuntu environment or something of some sort. But it's not really the Mahuika we know. And that particular environment has the tools that I need installed. For instance, MPI i4, which is the compiler that Alena mentioned, and it's installed. It's not a module, right? I don't have to do module load there anymore, but it's definitely available there. I can do, and it's definitely working, so I can check that it is working actually. I just type in version, and it's 2021. It's a recent version and so forth. So that's how things feel. I can do NeSI no backup and essentially see everybody and be able to access any of those directories where I might have data or I might have code. Now the next thing we will just illustrate, and I think we might be running out of time, but I'll show you how to use that. What I want to show you is how to use that environment to actually build a code, which, using those compilers, but, on Mahuika, because for some reason, maybe it's a closed source code or something. In this particular case, it's not closed source, so it's I can just do the clone of git at github.com, and then it's my username, and then it's called Fidi Bench, but it really could be any code. So we'll just do the cloning of that particular thing. So I could do that. Actually, I could have done the git inside the Alena as well. It would have been the same thing, right? So maybe let's go back to that shell. I'm still in the same directory. I can still do ls. I can see Fidi Bench, and let's imagine that I'm going to build a version of that code. Don't worry about what it is. But in my container, I have CMake that is installed, and I can do this, but I want to specify the compiler. So I want to say cxx is equal to the MPI cxx, and maybe I have to specify the Fortran compiler as well. So it's MPI i4. And I think, I think that looks all right. Let's see. So now I'm just building essentially the code using the Alena environment. It just works just like on a normal Linux system. It detects some stuff. We don't have to worry about it. We're just going to compile the code. It's going to take maybe 30 seconds, whatever. And then we're going to run it inside the container. It's going to run it happily. And then we're going to run it using a slurm command outside the container and see how that works. So, you know, some stuff gets built. It's all good. All right, it's all good. So essentially now inside the container, I know where the that stuff is installed. So I'm just going to call that executable. And, you know, it does some stuff. It's a finite difference little model that does some advection and a couple of time steps. Everything is hokey pokey. We're happy, right? But now we're going to exit the environment. So we go back to our sort of traditional environment. And what we can then do is, so let me just go back to one of the slides here where we basically it's very small. Let me see if I can make that bigger. All right. So basically, we're going to type this command. We're going to execute that. So we have the C file which is here. We're going to have exec. And then we're going to load essentially the or bind, I should say, slurm lib64. We still need to provide the application. So the application was this, right? Right. So let me just move that a little bit. And we want to do that in Slurm. Okay, and so we're going to say, well, I'm just going to do the S run. Okay, I'm going to run on Milan, let's say, but I could run locally. And I'm going to specify a number, maybe just one node for the time being. And then we're going to specify, tasks. And we're going to have 8 tasks, for instance. And I think that should be enough. Alena help, exec. Okay, so something I didn't do that. Alena exec. Only one received. Okay, let me just make that a bit bigger. Must have, oh yeah, I think some sort of, oh yeah. So forgot to put a space here. And now, normally I should write a NES batch script and so forth, but you know, I'm taking a bit of a shortcut, so I just do the S run and passing the normal S batch arguments. And so now we're just waiting, you know, for the and for some reason I made the same mistake. Let's see, maybe I have to give up wind. Okay, that's it's the build directory. I think that's missing. Wait. Okay, okay. Let me just fix that. So TMV here. We're just going to check that we're passing the right. I think I'm just missing something here. Because when I exited essentially my environment, I want to be sure that that the path is correct here. So I'm just going to copy paste that. Sorry. So Bing. Hopefully this will work now. And now we're running and we're using 8 processors as expected. Now, in order to run with on multiple nodes, it's not quite clear whether Intel has to be loaded or not. It seems to have been happy to run without. But there's this environment variable, which is quite small here. Make it a bit bigger. And this setting this environment variable by _MPI fabrics and set it to OFI. So I just do an export here. And now what we're going to do, we're going to run that same command, but now on 2 nodes, hopefully, that will maybe get having more processors, or we keep the same, that's fine. Waiting a little bit longer, but happy, for people to take to ask questions or do anything that would or just ask anything that they have on their mind. Maybe the last thing that I can just say is that if I just try to run the executable, it's not going to work, right? That's because it needs essentially the environment of the container. So you can see that you have this shared library, MPI, all kinds of stuff. Typically missing because the software inside the container does not match the environment. And chat, let's see, more questions maybe.
I ask another one?
Yeah, absolutely. Go ahead.
Thanks. All right, so I can see now that my earlier question was a bit off base. So you've just trying to make sure I understand what you've done. So you've built a container that contains everything this executable needs, and then interactively, you sort of inside that container then built the application.
Yes, and I build it on the file system that is outside of the container.
Yeah, that's cool. Okay. So would you expect that is the way that most researchers would work, rather than building a container that contains the executable as well?
I think the second option is desirable. It's a desirable one because then you have the executable and everything, and you can do that. It's just that the way we build the container, we're using that Git flow, and so we write the definition file, and then we have a hook that creates essentially the container for us automatically and stores it on the web. But if you do it manually, then and you can download the code and essentially install it inside the container. That would work as well.
Oh yeah, okay, understood. Thanks.
Can I do a quick comment here? We're still model developing our code, so that's the reason why we constantly recompiling and changing it. So that's why we wanted it out of the container itself. But
good point. Yeah,
I would assume even us, once we lock the code, we would be able to shove it in there and just forget about it whenever that happens.
Yeah,
that makes sense.
absolutely.
Thanks.
Yeah. I mean, that's a good point. And sometimes, some things sort of change. And as I said, a container is frozen. And so you'd have to rebuild the whole thing, the whole tool chain, essentially, if you just change one thing. So it's a question of it's a question of granularity in some sense. What's the best, right? I mean, I think in the case of Alena and Alexandra, it takes maybe an hour to build the coupled model once you have the whole environment, but it takes a few hours to build the whole environment. So we decided to sort of split the two a little bit. But it's a choice. It's a choice. Yeah.
Yeah, that's great. Thanks.
Yeah, so thanks everybody. I think we just we have five more minutes, but if people want me to type something or try something, be happy to do that. I think we yeah, we ran using 2 nodes and that particular environment. But I can maybe show you if what happens if you don't set that environment. Why not? And you so that unset. Sorry. Yeah, shouldn't put that. Okay. So now we unset that variable and then we run maybe the same command as before, 2 nodes. It should run with 1 node, but well, it did run. Maybe it did run on 1 node. And I have to check because obviously it's a pretty small application, but I can change the number of cells and increase them to, I don't know, 12 or something like that, and then have vastly more processors here, 64 something, and then 2 nodes, and then I think I have to increase the memory in order to run maybe I don't know, 20 gig or something, hopefully. So we'll see if that works. I'm taking some risks here. I'm going sort of off track a little bit. Yeah. The other thing that we can mention is that Alexandra Gossart, Alex Gossart was able to run that very same executable. So she was able to take the container and the executable as it was compiled on Malyarenko and run on Rapoi, which is the cluster at Vic University, but I believe, if I recall the situation, you were only able to run on a single node. Is that correct?
Yes, that's correct.
So we don't exactly know. So maybe the fix which I'm mentioning here may not necessarily work on another platform. It's sort of a bit of trial and error, but yeah. I think there is a mechanism by which essentially the MPI inside and outside can communicate and hand over essentially the call to go out, and it's this library called the lib PMI, but I don't know too much about it. Well, thank you, everyone.
Alex, could I just ask one more question?
Oh, yes.
If we have time. Sorry.
Go on.
Related to portability, I guess this might be something I missed at the very beginning as well. What determines what bits of the external file system can be seen from inside the container? Is that specified at build time or when you run it dynamically?
The latter. You can specify. So on NeSI, we're going to automatically bind the /NeSI no backup and project directories for you. But you can mount additional directories with the -b command option when you do
Right.
obtain exec.
So that's what you've got on the command line there. Okay, that explains that.
Yeah.
Yeah, that's good. I was thinking it couldn't be as portable as you were claiming if it was a build time configuration option.
Correct. Yeah. And I mean, it's got to be like Intel processors, and there are some caveats. But it's I think it can be fairly portable, much more portable than what we had before. Keep in mind that Maui is really a very special architecture. It's the Cray XC50, and it has a Cray environment, and it has all kinds of other things. And one thing that Alena sort of told me, and Alex told me recently was that, hey, but it's so much easier to actually build on within a container, because it's a very vanilla standard environment, and if you run into issues, then you can immediately search the web and Google
Yeah.
And then, when we get the new Genoa processors, should be able to run just as is. We'll check that. Hopefully, I'm not going to bite my fingers and say, no.
Yeah, famous last words, Alex.
Yeah.
Forget about the last sentence.
On that note, thank you so much, everyone, for sticking around with us until the end. And if you have any additional questions, please feel free to email us. And I swear I've got an email ID for you, which is support@nesi.org.nz. I had that on the slide, but now my Zoom is frozen. Consider emailing us if you have any further questions, and you would be getting a feedback form in your email soon. Do let us know how you like the session, and if there's anything we would like to, we should be improving on, let us know. And on that note, thank you.
You.
Thank you. Cheers.
Bye.
Bye.